go back and maybe kind of review where that came from. Okay, that's the peak value of that. So it would be that times cosine omega t. Okay, but the peak value is that b in peak, if you will, b in peak. Is that term? Okay. All right. So now, how did I make a decision? Well, if I know I have to get to 400 volts, if I go to my web page over here, go to the web page over here. All right, that means this guy's the group I want to go from. For sake of argument, and in the lab you have a little bit more to go from, I'm going to go with C equal to 0.047 microfarads. C equals 0.047 microfarads. Now, this circuit here has its peak when omega equals 1 over root LC. Okay? So what that means is I've got my C picked. I know what omega I want. I can solve this for L. If I do that, I see that it's 599 microhenries. Okay, I can then do a calculation to determine the number of turns that I need. Okay, how would I do that calculation? Well, N is equal to the square root of L over whatever the AL is. Okay, well, what kind of core am I going to use? Well, good question. If I go back here, let's say I picked this T400 core. All right, that's the same one I think I used in the previous example. It's this AL is 131 nanohenries. So if I go through and do the calculation, that gives me 68 turns. Okay, so I need 68 turns of wire to make that happen. Okay, all right, and you guys will do that. So I know I need that. But going back to last time, we basically said what I need to do is need to determine how big a voltage I need. So I need to have 400 volts in order to strike this lamp, according to what I said in your example there. All right? And I have this 40 volt source, which means V in peak is this. So what we said last time is that in order to make this thing work, the circuit needs to give me a certain amount of gain at this frequency, omega equal 1 over root LC. Well, how much? Well, V in peak times a peak gain I'll call P has to be equal to 400 volts. All right, so at a minimum, if V in peak is 4 pi times 40 times a half, okay, what that tells me right away is that P has to be at least 15.7. All right, so 15.7 is the minimum. Okay, now, what limits the gain? Well, we said this last time. Basically, this thing's got some RC and this has got some RL. Now, RC is easy to pick, okay? So, let's say if I look at that data sheet, what I may find is a pretty reasonable value for RC can be determined from the data sheet, okay? So again, what did I say? Well, basically, I have this thing we call the dissipation factor, or that tangent, that loss tangent. All right, that thing was defined as RC over XC, right? So RC, the real part of the impedance, divided by the imaginary part of the impedance, 1 over omega C. Sometimes instead of saying the imaginary part of the impedance, say the resistive part divided by the capacitive part. Okay? Now, if I look at the data sheet for this thing, what I'll find is that it's at 1%. Okay? So that means that the resistive impedance is 1% of the capacitive. Okay? So I can plug in here my omega equal to 30, so omega equal to 2 pi times 30,000. Okay? And I can plug in C equal 0.047 microfarads. All right, and then solve for RC. Okay? If I do that, I get RC equals what? 1.13 ohms. Okay? All right, so now, at this point, what I know is the following. And again, if you missed that calculation, it's there in your notes, so don't sweat it. I got this source here. I got RL and I got L. I got RC and C. Okay. Now, this is 0.047 microfarad. 0.047. This now I know is 1.13 ohm. Alright, now, what we did last time is we basically wrote out the transfer function for this thing. I don't quite remember what that was. It's something like this. SRCC plus 1 over S squared LC plus SRC plus RLC plus 1. And I could be wrong, so don't take me verbatim on that. Alright, that's from here to this output. The in to the out. Okay. Alright. Right now, can I say what RL is? Maybe, maybe not. Alright, it turns out it's actually a little bit hard to sort of say what it is. Alright, because when it comes down to it, RL is this core loss term. Okay? Alright, so remember something we've said pretty clearly now. If I've got 400 volts across here, I'm basically going to have 400 volts the other way across here. Alright? So at that point in time, when I've got 400 volts across here, I can figure out the peak B field that gives me with that 400 volts. And I can use that to figure out how much RL I've got. So the way I look at this is the following. I'll go into MATLAB and I'll play, I know what RC is now. Okay, RC is 1.13 ohm. I'll play with RL and see at what point does this thing give me enough peaking. Okay? What's the bottom limit? So if I put in RL equals 0, this thing will have a huge peak, way above that 15.7 that I need. Alright? When the peak value of this is 15.7, what I find is that RL is equal to 6 ohms, just about. Okay? So in other words, that's to hit the minimum. RL has to be less than 6 ohms. Okay? So we need to make sure our design gives us an RL less than 6 ohms. If it doesn't, we've got to start over. Okay? Alright, so let's try to make some sense of this. Okay, so how do I deal with it? Alright, well, we know for our inductor, based on what we said previously, that N is 68 turns. Okay? On this type of cord. So 68 turns. Now, we did a calculation previously that said the peak value of B was equal to the peak value of the voltage divided by N times A times omega. Alright, now let's be careful about that. What's the peak voltage? Well, suppose that we got 400 volts across this guy. 400 volts.